ionospheric aspect, and more specifically on the ionospheric delay, which constitutes one of the most important and decisive factors in the error budget. So we could get error in positions extending up to tens of meters under certain circumstances. So the ionosphere is what you call the uppermost part of the atmosphere, or the upper atmosphere as we call it. It owes its existence to the fact that the sun, of course, emits radiation, which ionizes neutral atmosphere, only a small portion to be exact, but sufficient to affect radio waves that go through it. So you can see that there is significant variability from day to night on the electron density with respect to altitude. So apparently all the radio signals that go through the ionosphere from MEO satellite orbits traverse this electron density region, and we get these effects that are reflected on the error in position. Of course, the ionosphere has an extensive range of applications that it affects, extending from radio absorption to an array of systems, interference, total blackout of based on excessive absorption during some particular intervals during the day. But mostly what we are interested in is the propagation delay it imposes on these radio waves that go through the ionosphere to reach our single frequency receiver, which attempts to get its position in order to draw information on that will be exploited by some applications. On an excessive end, you also get scintillations where you get complete loss of log of the signal. And as a consequence, we may have to reinstate a phase where we have to get locked to our receiver again. So one of these applications, of course, is aviation. There is a significant impact on critical applications like aviation. And not only the electron density, the pure electron density can impose a problem in the determination of position, but also in more sophisticated applications like dual frequency augmentation systems that can be affected by motion or gradients that exist in the ionosphere. So it's a byproduct of the physics of the ionosphere. We get this wave activity where we get strong spatial inhomogeneous structures in the ionosphere, where even sophisticated systems like augmentation systems based on sophisticated equipment like dual frequency receivers can undergo problems and discontinuities in performance and service. And of course, I refer, as I said before, we have these ionospheric irregularities that are more common in some parts of the world, but also over Cyprus at some points. That's why I'm offering this reference, which could create a loss of log. And this is of course critical because at present and also in the near future, aviation will have GNSS navigation as one of its most important procedures when planes approach, airfields. So one more common application is precision farming. Actually, Vasilis will give a more comprehensive overview of the arrays that are really affected and are relevant to our project, which are the single frequency applications, as I mentioned before. So depending on the critical parameter that we are trying to examine and also model in this project is the total electron content. So the fact that we have an increasing solar radiation intensity with respect to altitude and decreasing, let's say, density, molecular density with respect to altitude, we have a certain point of conjunction between these two opposite operating effects, and we get a maximum of the electron density at some point around 300 kilometers. Of course, this altitude actually varies, and this has a consequence to the algorithms that determine our critical parameter, which is just the integral of the electrons from the lowest to the upper height. Of course, we need to emphasize that during the day, as you will see also later in this presentation, we have a significant variability. So the electron density profile is depicted in this animation here from a real radar, from our radar over Cyprus during maximum solar activity, when you get maximum electron density as well. So you get that it extends significantly from day to night, covering a significant range of values. That's why we need to readjust from day to night our system to follow this significant variability. So as I've mentioned before, the critical parameter is total electron content measured in tech units. It's just the sum of the electrons that we can find in our path to reach the satellite. So from the from any ground-based system up to any satellite that is moving at any time, we can determine the number of electrons, which actually assert the effect on the radio signals that traverse the ionosphere and impose the delays that are detrimental to our positioning. Of course, the satellites are moving from low horizon positions to vertical positions at zenith, and so this affect very significantly, but always in accordance to the electron density profile that I have mentioned before, which varies significantly with altitude. So we are using sophisticated GPS receivers, not single frequency as commonly our mobile phones are, but dual frequency receivers, based on which we can exploit the fact that the ionosphere is a dispersive medium, so the velocity and the refractive index is a function of the frequency. So we can use two frequencies to infer the total electron content by exploiting the fact that our receiver can be sophisticated enough to receive both frequencies. So basically, although physically speaking, it's just the integral between two altitudes, this is what constitutes total electron content. We have this processing or calibration, as we more correctly call it, procedure to infer the total electron content via these dual frequency receivers. So typically, at the upper frequency, we suffer 16 centimeters of delay per one total electron content unit, which is 10 to the power 16 electrons per cubic meter. And at lower frequencies, the effect is actually higher. That's why some applications actually are subjected to much more ionospheric impact than others. For example, we have synthetic aperture radars that operate on much lower frequencies because they are monitoring vegetation coverage, for example. And those missions actually have to be subjected to more constraints with respect to the ionospheric impact. So we are lucky enough to have one of the oldest dual frequency receivers in Cyprus, installed by BKNG many years ago, to form part of the well-known IGS network that constitutes the backbone of the infrastructure that we are using as a dual frequency global network, using many applications. So we have a track record of more than 20 years of raw measurements from this station that has been exploited by many other researchers during the last, mostly during the last 10 years. So we were lucky enough to be able to study the ionosphere over Cyprus for over 2 solar cycles. So, and to get a good understanding of the variabilities involved over this station. And so typically, if we have a dual frequency receiver that can monitor the ionosphere, we can observe these arcs of total electron content. So as a satellite sets, we can get a maximum value of total electron content because our radio signal traverses through a longer path through the ionosphere. And as the satellite is moving towards us, of course, the total electron content reduces because it sees, let's say, less ionosphere in its path. And as it goes through the horizon to set through the other direction, through the opposite direction, of course, we have a total increasing trend again for the electron content. So this is just the raw measurements we process, and of course we need to calibrate these measurements based on the errors I have mentioned before. So for a 4 consecutive day interval, we see the full performance of our calibration method, the arcs. And of course, if we connect the lower points, we get the vertical total electron content, which is the content, the total number of electrons we see if we look overhead as the satellite passes over us. So this is the underlying data set which we have used to evaluate, let's say, our technique, and also to, in real time, we are using similar GPS receiver, dual frequency GPS receiver in order to provide the background that will decide what should be the correction on the next day. I will focus on this one during my next presentation. Of course, we need to emphasize that since we are talking about solar radiation, the solar activity level has a direct impact on the actual positioning, and of course, based on the impact it exerts on the ionosphere. So we have solar cycles that extend for 11 years. Currently, we are at the first stages of solar cycle 25. There is this discussion of a decreasing solar activity, which has been related to the structure of the solar geomagnetic field, but it's beyond the scope of this presentation. We just need to take into account that the lower the solar activity level, the less the impact we expect to have on our GNSS positioning applications. So this can be evident from these plots. So you see in red color the solar activity level and various critical frequencies related to various layers of the ionosphere here. So you can see that for the most critical layer, which is the F2 layer, the F2 critical frequency, as we call it, has a clear correlation with solar activity. And since the F region is the most important contributor to total electron content, you can also see this effect with respect to the solar activity level also in tech. So there is a very clear correlation between these two, between this index of solar activity and this number of electrons per cubic meter as we defined it before. But not only that, it's not only the sun that affects the ionosphere. We have secondary effects which are very significant based on where our receiver is located on the globe. So we have various physical systems that are mostly driven by the configuration of the geomagnetic field, also in conjunction, of course, with other phenomena related to the neutral atmosphere. So this is a complex system with interactions being generated from below and from above the ionosphere, but also in the ionosphere itself. So the ionosphere, as I mentioned before, extends approximately from 70 kilometers to 1,000 kilometers, with an expected peak around 250 to 50 kilometers. So all these variabilities constitute characteristics that are very closely related to a specific point on Earth. That's why our mitigation algorithm is very, very specific over Cyprus, but can be applied in other parts of the globe if the instrumentation exists. So in order to understand the significance of the variability scales that we are discussing with respect to this important parameter, total electron content, just to emphasize that it depends on various time scales. There are long-term solar activity-driven changes, seasonal variation changes that are also related to the neutral atmosphere, diurnal variation changes that are mostly related to the solar radiation, but also to the background, day-to-day variability, which imposes a limitation also for the ionospheric correction algorithms, and I will try to reflect on it on my second presentation, and very short-term variations that could be attributed to the impulsive behavior of the interplanetary medium as well, so the part that connects the sun to the Earth. So depending on the most significant variabilities, we can see that so here we have 30 days of a certain month of total electron content superimposed one over the other. So during low solar activity, you can see that the range of variability is very low. And as we proceed through the years towards a high solar activity regime, you can see that for all relevant months of that particular year, 1990, that was a high solar activity year, an excessively high solar activity year, as we've seen in a couple of plots before, you can see important variability. So this means that the algorithms that determine the single frequency positioning have to struggle during high solar activity years and can perform to a relevant extent better during solar activity years. So you can see that there is a solar activity effect, but also a seasonal effect. Okay, so we expect different variability during the summer than winter, and this of course changes based on the location, because the spatial variabilities are also very critical with respect to the ionospheric medium. So we divide, let's say, the global area in different latitudes where different physics actually are coming to play. So of course, all of them have their challenges, but the mid-latitudes that Cyprus resides, somewhere here, is the most benign, let's say, regime. So at low latitudes and also in high latitudes where the magnetic lines of the geomagnetic field are open and therefore energy can flow in, we have the most challenging, the most challenge for the models to respond. Last but not least, of course, is the impulsive behavior of the sun. As I said before, the sun also emits particles that form the solar wind, traveling at, let's say, hundreds of kilometers per second, reaching the Earth, which is protected by a geomagnetic shield. But because this configuration of the geomagnetic field has its peculiarities, some energy can flow in and directly affect the ionosphere. And this is the driver of the short-term effects that we experience. Of course, sometimes they can last for days, and where we have significant detrimental periods of positioning. And this is where the single frequency algorithms have to respond to it in a challenging environment. This is an example of one of the great storms in 2003. And you can see a chain of dual frequency GPS receiver during the benign phase and during the extreme solar impact phase. You can see to what extent all of these stations have been affected from this significant geomagnetic storm. So this animation shows, again, to a global extent, during a storm, an ionospheric storm as we call it, which is a byproduct of the geomagnetic storm, how significant the effects of electron density increases are. So with respect to the fact that the single frequency correction algorithms cannot account for these changes, the concepts that we discussed in this project are significant, not only at its present form, but also in its future form, which we aspire to develop it. During my first two slides, I referred to this wave activity that is manifested in the ionosphere. Although we are talking about a fraction of a 10th unit, this can be very, very significant when we are trying to operate in the field, as in order to determine our position, even in critical applications like framing vast areas of land and determining accurate positioning locations. These low fractions of 10th unit waves that are propagating through the ionosphere can deem our devices not operable. So it's possible to lose lock during these intervals and not being able to achieve the grade of service that we aspire in order to develop to determine our position in detail. So the project focuses on the Galileo system, on the Galileo ionospheric correction algorithm. And we are trying to, let's say, operate on an approach to determine what to expect the total electron content will be during the next day. And by mitigating this effect to try to reduce our positioning uncertainty. So the drive for this project came out of a study that we did concerning years of data that we were able to collect during the past 10 years, 20 years actually, but exploited it during the last 10 years. And it was clear to us that the underlying neck-quick configuration doesn't follow the variabilities over Cyprus very well. For example, during September, we see that the measurements over Cyprus exceeded by far what the underlying specification of neck-quick was. The opposite effect during a different solar activity regime. And of course, we thought that based on augmentation systems that also exist and try to, let's say, mitigate in part of this error could be the solution. This is just an example to show how a satellite-based augmentation system can minimize the ionospheric related error with respect to a standalone GPS receiver. So we can see that it can have some impact, some positive impact in that error, but it's still a significant error with respect to our let's say, benchmark of the ideal GPS receiver being augmented by this satellite-based system. I don't have the details to go. I don't have the time to go to the details how a space augmentation system work, but I mean, at the time we also were able to see that the Gnss augmentation system that it's operates over Europe that does not cover Cyprus very well. So single frequency receivers operating in Cyprus would not benefit from this augmentation system. Of course, lately there have been some efforts to install rim stations that actually control the accuracy and the grade of service of this Gnss augmentation system that could enhance the performance over Cyprus, but this is still not the case. So also with respect to continuity and availability, we have observed that there could be some issues. Just to cover the whole topic array, to a satisfactory extent, I just need to also discuss scintillations a bit. These scintillations are the extreme manifestation of the ionospheric impact. It's due to inhomogeneous structures in the ionosphere. Of course, as we progress, we are in the position to determine much more phenomena because we have a lot of satellite missions that can give us a different view of the ionosphere. Even over Cyprus, that we thought that that could not be a case of a significant strong inhomogeneity. Through our research during the last years, we were able to determine that this is not the case. So the more instruments you have, the better analysis you can make and characterize a region. So as I said before, the important aspect is that scintillation can cause complete loss of log of the signal. With respect to the loss of log of signal, of course, this can be also an effect of jamming. So during the last, let's say, year or 1.5 years or so over Cyprus, we have experienced these jamming effects, possibly attributed to Syria conflict, where, on the forces are trying to jam the instrumentation of coexisting forces. So anyway, scintillations are very important. Just to end my presentation with an example of what scintillations are to a global scale, the effect that they can cause on an actual operational system. When you get scintillations, you lose loss of log, and you have to reestablish your log with the receiver, which could take some time. For some applications, this is quite critical. For most applications, not, but for some, it's quite critical. So through our scintillation monitor that has been operating over Cyprus during the last 6 years, we were able to determine such events, which were ionospheric driven and not of a technical, let's say, origin imposed by intentional actions. So you can see that at times, during some particular events, we get severe scintillation activity over Cyprus, and this is where some critical, critical infrastructure may not operate up to the standard that we expect to. So I hope I have covered, and I gave you a brief understanding of how the ionosphere affects positioning systems. And during the next presentation, I will discuss more about our project.
Thank you, Haris, for your presentation. It is very important to know how ionosphere affects the positioning systems in order to fix them, of course. Just a little information. We are recording this presentation and the speakers and the conversations for our archive. Now we can proceed, Haris, to the next one.
Okay, so in this project we have collaborated. It's a collaborative project between GeoImaging Limited and Frederick Research Center. The purpose was based on the discussion, the presentation I just gave, to try to find ways to develop a framework based on which we will establish, let's say, an idea that could develop further on a global scale, and based on which IoT devices as well, not only mobile devices, can exploit on a local scale in order to address this ionospheric uncertainty and try to mitigate it to a certain extent. I need to emphasize that the purpose of this project was not to develop an actual application, but to form the framework and make sure that this framework works, actually is operational, and it can provide the basic inputs to any future developers that want to exploit this idea in Cyprus. And if we are successful enough to export this idea in other parts of the globe where the instrumentation is in place to allow for such an idea to be applied. So based on what we know, of course, these satellite systems that we have discussed before, GPS, GLONASS, Galileo, have an embedded algorithm to mitigate the ionospheric error. So by broadcasting messages that contain information relevant to the applicability of this algorithm within the mobile device that tries to determine the position, the mobile device or any chipset tries to account for this expected value of error and reduce the mitigation by mitigating when it automatically solves the positioning equations. So the NetQuick model is a model that was devised many years ago. It has been revised a number of times, and it has been adopted as the official model to describe the ionosphere within the context of the Galileo satellite system. So based on this idea, of course, any satellite receiver, any single frequency satellite receiver can determine, as I said before, by a minimum of 4 satellites position. And of course, looking at different directions where the satellites are situated, you can actually sample a different ionosphere. And this information is embedded in the model itself. It's a semi-empirical model, so it is based on a lot of data that have been assimilated throughout the years and have defined descriptive functions to map the variabilities in the ionosphere. So the NetQuick G, of course, was it's the actual algorithm that is embedded in the chipsets, and it is based on the NetQuick model, but also has been subjected to some modifications. So it can provide the electron density at any particular point over the globe within 0 to 22,000 kilometers over the surface of the Earth. And so by driving this algorithm with these broadcasted messages that the satellites actually broadcast, we can determine the error and mitigate it in the chipset while it is attempting to solve the equations of position. So it's an open source code. This is what we have exploited in order to be able to apply our experiments and formulate our idea based on this algorithm. So the key aspect that we need to appreciate, of course, is that since the solar activity is an imposing factor on the electron density at any point over the globe, actually, one of the parameters that the satellites broadcast is the ionization parameter, which is described by a second-order polynomial with respect to the modified magnetic latitude, which is a special coordinate which takes into account the geomagnetic field and its structure. So normally, based on extended experiments that have been done, most of the total electron content values, when you try to apply this second-order polynomial, will fall within a short distance with respect to the optimal value of the ionization level with respect to the coordinates, actual coordinates of the receiver. So basically, this is just a representation of the solar activity of the day in question. And how this NetQuick G algorithm actually develops its operability, it's based on the data of the current day. By assuming that next day things will more or less be on the same ionospheric level, we provide the parameters that the receivers will be on a global scale will be able to operate on the next day. So this is, of course, based on some specific dual frequency like the Nicosia station I had mentioned before that operate for 24 hours during the previous day. They sample the ionosphere over their region, and then all this information is sent into a common server that will try to optimize the ionization level, which, as I said before, is like an indication of the solar activity. And then the system will actually broadcast A0, A1, and A2, which are the 3 ionization parameters. So every day, when you are connected to the Galileo system through your mobile device, you are also receiving A0, A1, and A2 continuously. This can also actually change within the day up to 4 times, but this is not typically the case. Usually they stay constant throughout the whole day. So our mobile device can receive this information, and by applying the net-quick model, can account for the uncertainty through the total electron content estimation. So what we have attempted in this project is to exploit the fact that over Cyprus, we also have the capability to infer the electron density profile with great accuracy. So this is not, of course, a situation that applies in every part of the globe. This is a consequence of the fact that we have a specialized radar that we can exploit. So every 5 minutes we are sampling the ionosphere over the island. So instead of receiving A0, A1, A2 from the satellites, the idea is to optimize a local-based ionization level and provide the parameters to any developer that would like to exploit them. And of course, this is related, as I said before, to the trend that is the upcoming trend based on which our mobile devices have significant processing power that can enable them to determine positioning on a software level and not on a chipset level. So this is a particular requirement for this idea to be exploited. So typically, the ionosphere, the global ionosphere, has been condensed into 12 files, one for each month, based on data that have been gathered a lot of years ago, actually, where HF communications was the principal mode of long distance communication. Radars like the one we have in Cyprus existed to a great numbers over the globe. But of course, with the advent of satellite communications, the interest has declined. And also optical fiber capabilities. But based on these years of measurements, the scientists at the time were able to compress, let's say, the ionospheric behavior into a number of files based on these 2 critical parameters. I'm not going to discuss in detail. I've mentioned FOF2 before. Is the critical frequency of the F2 layer. It represents the maximum electron density of the layer. So based on the Fourier time series on a limited number of coefficients, scientists were able to describe the variability in time with respect to time based on 13 and 9 coefficients for these 2 parameters. And they also used some specialized space polynomials to match these values in space. So they have used more than 150 stations. So the accuracy of these representations was quite good, as you also can find out even today when we try to validate those coefficients. So with respect to solar activity, the idea was to interpolate in between the lower and solar activity linearly. So what we do today, the way we apply the algorithm today, is based on this very, very simple idea. So, and the problem is that for Nicosia, for Cyprus, let's say, if during our effort to optimize with respect to our position, the ionization level, sometimes we see a great significant distance of the actual ionization level we apply, which is here, and the optimal value which holds over Cyprus based on measurements over Cyprus. So the idea, of course, was to forget about this optimal curve and focus on a more localized solution. So in order to do so, we attempted two avenues. One of the avenues is to work on the long-term level, and one which was preferable, of course, based on the established variabilities of the ionosphere, to work on the short-term horizon. So we tried to embark on both avenues during this project. So the first approach was to try to formulate the coefficients of the CCIR coefficients over Cyprus in the long run. And in order to do so, we have gathered our ionospheric measurements from our radar. For a number of years, we have meticulously manually scaled those, and we determined the higher solar activity regime and the lower solar activity regime of the variability of these two parameters, which is FOF2 and M3000F2. And we tried to reformulate based on the same number of coefficients because we didn't want to mess with the structure of the underlying NeQuick-G algorithm. We just wanted to see if with the same number of coefficients, we could express in a better way the long-term median variability behavior. And these are the results. So as you can see, we could very into a satisfactory extent, let's say, express with the existing number of coefficients very accurately and reproduce the median behavior of the model. So we were very satisfied about this result because apparently it could offer, even in the long run, even if we replaced in our mobile phone the 12 CCIR files with the 12 CCIR files out of our analysis, we hope that we could achieve significant improvement. And this is reflected to a long-range study we did using a full year of RINEX files over Cyprus and forming the differences between the Cyprus CCIR and the standard CCIR as it operates today. We were able to determine that there was some appreciable gain out of this approach. So the other idea, of course, was to exploit our radar, which we are using to sample, to infer the electron density per altitude, and go to a short-term solution, which is, of course, more demanding, but it could pay dividends as we hoped for. So the idea here is to operate on a day-to-day basis. So get the ionograms, get the raw measurements from our radar, try to auto-scale them because we don't have the luxury to have a manual intervention, get the parameters on a daily basis, and then use a collocated GNSS station that we explicitly installed for the project to determine the total electron content data, optimize AZ, and use the short-term CCIR files and optimal AZ values to run, to make these values available to any application that was able to exploit them. So this is the second aspect, the short-term aspect of the framework that we try to achieve. So of course, when you get for 24 hours the values from the radar, you have uncertainties. If you have a long gaps of uncertainties, then the actual Fourier approach breaks down. So we attempted to mitigate this by using an X-square minimization approach in order to have a better performance during this long series of missing data, which could be the case. And this proved to be a better solution. So the idea, this is just an example of a particular day. We are optimizing here by varying the A0 value. Only the A0 value is sufficient to express the local ionization conditions, and we achieve the minimal value that we are using that we are making available to the actual users that want to exploit this value to determine their positions through software means in a potential application through their mobile phone. So you can see here that indeed the optimal solution of about 118, I think, here was the one that provided the best match to the actual measurements. So this is how the system works, let's say, as it is now. And this is the idea which is applied, which is similar to the idea that the NetQuick-G or standard NetQuick-G applies. But as I said, by optimizing the parameters on a local scale. So this is some results that we can see. The blue curve represents the actual measurements of total electron content. The green curve is actually the standard NetQuick-G as it operates now. The red curve is the long-term solution that we have devised, and the orange curve is the actual short-term solution. So you can see that this is a 4-day interval for consecutive days. So, I mean, for some of the days, of course, we should be able to show the previous day to determine whether this orange curve follows the blue curve. So this is not very ideal, but in this case, you can see that the orange curve actually that was determined based on the blue curve of the previous day, followed the actual day measurements well enough. And the important thing I would like to emphasize here is the fact that you can see how variable the ionosphere is from day to day. That's why the single frequency algorithms fail to a significant degree over particular locations. I mean, Cyprus is a typical location which is affected by various low latitude variability regimes. So it's not very characteristic of a mid-latitude benign region. So you can see from day to day total electron content very, very significantly. Not always, of course. For these two particular days, the blue curve is more or less similar. That's why our algorithm has time to adjust and express well enough the data, which also coincide with the long-term solution. So when things are as expected, the long-term solution also behaves well. The challenges, of course, arise when you have this variability being manifested to an extreme extent. So this is an example here. So you can see that the orange curve more or less follows the blue curve of the previous day. So this means that we have managed to capture the previous day variability that we expect to hold for the next day, but it doesn't. That's why things don't work out so well here. Actually, on the next day, which is quite different than the previous day, our algorithm attempts once more to adjust, and it adjusts variously well, relatively well. But you can see that the ionosphere on the next day actually changes again. So that's why you can see that there are still challenges with the existing approach. Of course, this is an extreme example, but I thought I ought to show it. So that's why the logical next continuation of our project is actually to be exported to other parts of the globe. So because it's actually a cloud-based solution, if we just get a stream from any of these radars that exist all over Europe, based on the spatial let's say, correlation in the ionospheric medium, which is around 1,000 to 1,500 kilometers, we could cover the whole Europe by just establishing a stream between the radar and a collocated GNSS station. And also that idea could be, as we aspire to actually experiment with the idea on a global scale, you can see that the coverage of these specialized radars is quite well over the globe. So we could extend this idea to a global solution, even operating on a real time mode, if we succeed in receiving information in real time from these radars, not only from the previous day, but if we achieve to disseminate the information they provide every 5 minutes, then you can correct the ionosphere as it goes. So this means that these cases will be avoided if we succeed in establishing a real-time solution. Thank you very much for your attention.
Thank you, Haris, for your great presentation about our method to correct the iono delay. So let's continue with my presentation. Let me share my screen. Can you see my full screen?
Not yet.
Not yet.
I can. Now, yeah.
All right. Let's start. I'm Vasilis from Geoimaging. We will see the current and emerging single frequency positioning applications. Let's start. So at first we will see some market facts and predictions about the future. We will see some GNSS applications, the categories that GNSS is applicable. We will see some examples, and in the end, we will see the in-app raw measurements that is available on every phone, and the ionospheric corrections that we can apply to them. So, global annual GNSS receiver shipments are forecast to grow continuously across the next decade from 1.1 billion units in 2019 to 2.8 billion units in 2029. The majority of shipments is represented by mass market receivers costing less than €5. These account for more than 1.6 billion units in 2019 and are set to grow to more than 2 billion units by 2029. 90% of the receivers in this price segment are used for smartphones and wearables. It is worth highlighting that out of 1.7 billion GNSS shipped units in 2019, more than 40% was Galileo enabled. That is very remarkable and promising result. So what about the revenues? Services relying on GNSS technology to create added value for users represent the biggest revenue stream for the GNSS market. In 2029, revenue from added value services will account for 166 billion, or more than half of total global GNSS revenue. Let's see the specific segments of the revenue. The road and consumer solutions segments dominate by far all other market segments in terms of cumulative revenue, with a combined total of 93.3 for the 2019 to 29 forecasting period. In the road sector, most revenues are generated by in-vehicle systems, advanced driver assistance systems, and fleet management, whereas consumer solutions revenues mainly come from the data revenues of smartphones and tablets using location-based services. More than 50% of the remaining revenue will be generated by agriculture and geomatics. The main revenue generating applications in agriculture are variable rate technologies and automatic steering, while the primary source of revenue in geomatics is cadastral and construction surveying. The wearable market is, of course, on the rise. Leveraging the hardware as a platform, software and apps provide endless opportunities to tailor the use of position to the needs of mass market users. Wearables represent the beginning of the separation between smartphones and end users, as an increasing number of smartphone services and apps are now accessible via new interfaces like smartwatches, fitness trackers, smart glasses, and clothing. According to Statista One, connected wearable shipments are expected to reach 64 billion by 2022, representing 1 billion connected devices. Currently, wearables are mostly used for fitness, health, and entertainment. The different categories that Gnss applications can be used is, of course, navigation, route planning, and turn-by-turn instructions enabled by Gnss for both pedestrian and road users through their smartphone. Of course, mapping and GIS, geomarketing and advertising. Consumer preferences are combined with positioning data to provide personalized offers to their potential customers. Safety and emergency. GNSS in combination with network-based methods provides accurate emergency caller location. Enterprise applications. Mobile workforce management and tracking solutions help companies to improve their productivity. Then we have also sports, games, health, of course, and personal tracking and social networking. Now let's see some more specific applications. Different type of mobility sharing services make use of GNSS positioning for asset localization and transaction calculation, including asset sharing and rights as a service solutions. When these services involve sharing an asset like a bike, a scooter, or even a car, different business models exist. They can broadly be categorized into station-based versus free float, with the latter giving users more freedom when it comes to dropping the asset after use. For example, if we can rent a bike from a random point in our neighborhood, then we can leave it wherever we want in the seaside, for example. Focusing on rides as a service, these include commercial on-demand ride-sharing solutions such as Uber and carpooling services, enabling users with a common path and destination to share travel costs. Over the past years, it has become clear that GNSS is a key enabler for all these service and business models. Thanks to the positioning accuracy, availability, and reliability of GNSS that is essential for the users to find the assets and for the service providers to manage them. From the 1960s on, companies, individuals started to track their assets using computers and a variety of IT systems. Since then, technology has taken many steps forward, and GNSS-enabled trackers enable position tracking of all valuable objects, ranging from vehicles, heavy equipment, and materials to individuals, smaller devices, and even our pets. These GNSS-enabled devices are progressively becoming more miniaturized, smaller and smaller. Their usability is improving due to the advancements in both GNSS technology and battery life, which is kind of constraining when you would like to leave the tracker on your pet or an item. For example, in the case of high-value assets in transit, one of the key drivers for the adoption of GNSS is the increasing need for improved accuracy and availability, leading to the increasing adoption of multi-constellation solutions. Of course, autonomy wouldn't be possible without the GNSS, like the self-driving cars or any kind of autopilot, like UAV drones, or even swarms. In order for swarms to operate, the location of them is very crucial. Accuracy is very important for a precise and safe trip or emission of these. Augmented reality is becoming increasingly widespread with a variety of professional and leisure applications using digital content to complement and augment the physical world. And many augmented reality software developers are taking advantage of GNSS high accuracy for their localization needs. Augmented reality is a major emerging trend, the societal impact of which will be increasingly felt in the coming years. It is the future. New AR-enabled business models in the marketing sphere and in the industrial production, maintenance, and training, where AR solutions can make processes more efficient. An example of these applications is the LARA project that Geoimaging took part. LARA was basically a system that was guiding utility field workers by helping them see beneath the ground, rendering the complexity of the 3D models of the underground grid, such as water, gas, and electricity. In few words, the field worker was holding a tablet with a camera. He was looking on the real world, the pavement. Could see underneath the ground where the pipes of water, gas, and electricity was, even for repairing them or avoid them if they wanted to drill, for example. Then we have games, the availability of consumer GNSS receivers and GNSS-enabled mobile devices made possible the use of GNSS for gaming in the real world we are living. The oldest games and still the most popular is the geocaching that combines treasure hunt with trekking and outdoor activities. In this application, you basically have a map in front of you and you can see if there are hidden boxes, hidden treasures or caches. You will not find treasure inside, but you can discover the beautiful places they are hidden mostly in the mountains. And of course, we have Pokemon Go that is on the rise since 2016. I'm using both of them, and they are really. I'm really enjoying them. In Pokemon Go, of course, you go outside in the streets and you gather Pokemons. Then we also have health and safety. We can track vulnerable people like people with Alzheimer that are getting lost very frequently. Seniors that they want to send an SOS signal because they fell on the ground or they are lost. Also for emergencies where people get lost in the mountain or get hurt, even in the sea, or even for natural disasters. Last year's blind, visually impaired 8 people can really navigate through space with the help of GNSS and other sensors, of course. These are some examples. The possibilities are endless, of course. A really important development is as of Android 7, access is available to the GNSS raw measurements, allowing developers to use the carrier and code measurements as well as the decoded navigation from mass market devices. This allows for the creation of advanced GNSS positioning algorithms that enable the development of more ambitious smartphone-based applications. This means that you actually have access to the RF signals of the GNSS chipset. You also have access to the clocks and, of course, the measurements. And this gives the freedoms to deploy custom applications and apply the corrections like the ones we are developing in the serving project. A specific application that is made by ESA is the Galileo PVT app. PVT stands for position, velocity, and accurate time. In this application, you can basically, if you have Galileo on your mobile phone, you can visualize on a Google map your position from 3 different concurrent PVTs. The one with GPS only, you can use Galileo and GPS. Galileo only and GPS with Galileo weighted least square, the combination of these two. The configurable PVT atmospheric corrections that are used is NEQUIC. the one that we are trying to optimize over Cyprus in the serving project, and the global chart. These are for the atmospheric corrections. They implemented an equi-G model in a Java library, which can be executed on a mobile device and used by any Android application just by importing the jar file. This low computational complexity, and this is the first implementation ever running in a smartphone. So this is very important because having the freedom of raw measurements in combination with our correction files, we can achieve high precision with the positioning. And this is the kind of architecture that serving is targeting. equi-G consumes the alpha coefficients, the ionization parameters, and in combination with CCIR files that we prepare, we predict the total electron content that Haris talked before, which corrects the IONO delay. If we take a look at the architecture of this application, it's very important to see how this one works. We have with the green color the Gnss chip, which takes the raw measurements from the satellites. Then we have a server that provides these coefficients, the A0, A1, and A2, that are the ionization parameters. So in our this case, Google server provides them. Then the computation for the IONO delay is made by an equi-G with the blue color, and they also apply tropo delay computations. And then we have the accurate PVT computation. In our case, we can be the suppliers of these files, the coefficients and the CCIR files, in order to fit the equi-G algorithms that gives the IONO delay. And that's how we can provide these corrections and be applied directly on an application on any phone with a single frequency antenna. So that's it from me. Thank you very much. If you have any questions, we can discuss them, and we can proceed basically in the open discussion. Let me close the presentation.
Vasilis.
Hello.
Yes, Vasilis, this is Haris.
Hello, Haris.
I would like to thank you and Haris, for the excellent presentations. And I just would like to add to the conversation the point of view of the field engineers, let's say, that use the equipment in the field. And it's true that during the project, we found a correlation between the ionosphere activity that interfered, let's say, to our equipment, and the loss of log while we were out in the field, and we are using our professional equipment, the dual frequency equipment, and we lost log of the satellites, or some of our measurements maybe didn't get a fixed solution, as we say it, and as discussed with Haris and the others, we saw that there is a correlation that at the time that this happened, the ionosphere activity was pretty high. And I don't say that that's what affects the error. That's the only parameter that affects the error, but there is certainly a correlation between them. And also, I would like to say that in our field of work, a lot of our applications, especially regarding GIS applications or mapping applications, we very often use single frequency equipment like a tablet, a commercial tablet or a commercial drone. And it's very important for us to optimize accuracy. And so if we can predict the ionosphere activity and we can fix this error, I think it will all help us very much in order to perform our work better.
Of course, Haris, is very important. Imagine being on the field and taking measurements, and suddenly the positioning gets crazy, and you're using the global CCIR files, for example, that are not specific with ionospheric activity in Cyprus, and then you are completely losing the accuracy of your measurements.
And what we point out is that it usually happens same time during the day in a particular season. Let's say during May, June. As we saw previously in the diagrams, the ionosphere activity is pretty high.
Yes, this is the period of the high activity, let's say. So, if you have any questions or you would like to add something to the conversations, feel free.
So hopefully, Vasily, may I?
Of course.
So hopefully in the near future, we'll be able to find some interest from developers to develop and exploit our solution, and also we hope that we will be able to address this real-time solution, not only short-term solution, but also the actual real-time solution by exploiting our 5-minute radar measurements. That would be quite an innovation, I think. But of course, for that to have value, there must be developers that develop their own positioning solution applications in software, on a software level, so that they will be able to exploit. Because when we get this software capability, we have the luxury to interfere with the model. So not only, let's say, modify CCIR files or optimize the ionization level, but actually improve the model based on the local characteristics. Because these models have, as we said at the very beginning, they are semi-empirical models. They are mostly, their functions are mostly driven by data sets that are incomplete. And also, or they have not been updated because we had, during 2008, 2009, we have this extreme solar minimum that any model, including NetQuick, IRI, and some extensions of those, could not encapsulate what was going on in the ionosphere at the time. So in the ionospheric community, there has been quite some activity to readjust the models and to be able to respond to the extremes, the extreme behavior. And of course, in our case, it may be not so critical, but in other cases, like in satellite, missions, that they have to take into account the fuel they have to include in the satellite in order to be able to respond during its lifetime on certain maneuvers that have to be taken, or altitude readjustments based on the on the neutral density of the atmosphere that exerts some friction on the satellites that are usually moving on LEO orbits. So the friction is quite significant, and they could lose significant altitude at times. So for long-term predictions, these scientists are using these models. So it's important to readjust them. So if you are operating on a software level, you are very flexible to really optimize not only the solar activity impact, but also the physics of the functions of the model.
Yes, of course.
Yeah.
Yes, we have the equipment, we have the data, the technology advances with the recent advantages in deep neural networks. Of course, I believe we can find an even better solution and improve it even better, even provide the real-time corrections with our models. Like you said, now we are using short-term predictions. We advanced from the global CCIR solution to a long-term specialized for Cyprus. Then we improved it with the short-term prediction, and of course we can even develop it in the future with our experience and data with even better real-time solutions.
Mm-hmm. Yeah.
So, any questions or someone to add something?
Yeah, Vasilis and Haris, it's Kostas Smagas.
Hello, Kostas.
Thank you. Really nice, really interesting presentation of the results, and someone who is not technical can understand that there's a lot of possibility to get integrated with a huge emerging market. I just want to ask a simple question: if you have any immediate plans regarding a future project that integrates those new components that you have been speaking with, or do you have a partner in mind that would be interested in joining a consortium with you, maybe in the future? I don't know if Haris can answer that as well.
Yeah, definitely. That's why I showed these maps at the very end with these radars that are in operation these days. So, I mean, the next step for us to optimize the product and also find a way to verify through some open source, let's say, avenues and software that is out there, that we can really improve positioning significantly. So we are going to advocate in favor of this service through actual positioning performance, and because as Vasilis said, we have this availability of chipset nowadays that provide raw measurements, to try to find a way to develop an application, even as a pilot application, to demonstrate that this is a feasibly, positive solution towards improving single frequency algorithm positioning. Yeah. So there is room in the near future for development. Yes.
Okay, great. Thanks.
So thank you very much, everyone, for participating in this seminar. Thank you, Haris, for your great presentations. If you want to add something or ask something, send us an email. And sorry for the little delay, but I think it was worth it. So thank you very much, and have a good day.
Thank you very much.
Thank you.
Guys.
Thank you.
Thank you.
Bye-bye.
Bye-bye.